So we got internal alkyne reacting with H plus, H and water. So what happens here is if we number our carbons 1, 2, 3, 4, and 5, right? What's our nucleophile? What's our electrophile? Pi bonds nucleophile. What's the electrophile? H plus. The issue here, though, does it matter if I put the plus charge on carbon 3 or carbon 4? Is there any preference? They both bind to carbon. Is there really a preference? If I draw them both out, I'll put a plus charge here. Be a new H bond, or I could draw it like this. Number of carbons, there's 1, 2, 3, 4, 5. 2, 3, 4, 5. So is there any preference towards having a plus charge on 3 or 4? No. So both intermediates are equally as likely. Right? So because of that, then when we add in the next step, when we have water, right, in either case, right, water can attack either carbocation right, or it could attack here H plus. Right. So there's technically two types of, and then when we regenerate the catalyst, H plus goes away. Right. There's two types of enols that we could form, which basically also means there's two types of ketones we could form in the end too. So that's why there's two enols, two ketones. All right. So let's look at how we tautomerize one of these. So if I take one of these enols, and the H plus we just generated, right? So what we could do now is this pi bond can go grab that H plus. At the same time, these electrons come down. So if we had a 1, 2, 3, 4, 5. So carbon 3 is going to get another H. And then the oxygen and carbon 4 are going to form a new pi bond. We number our carbons, 1, 2, 3, 4, and 5. And then we finally regenerate our acid catalyst, but the H plus going away. Give the electrons back to the oxygen.
So the double bond happens.
So the first thing, so we have our star material and our product. We're going to analyze the product. We've got to look at what has changed. Easiest thing, the first thing to look at usually is how many, do we have the same number of carbons as we had before? So we've appeared to have added carbon. So if you said 1 and 2, looks like carbon 1 and 2 are here in the middle, right, where the action's kind of happening, where the pi bonds are at. But looks like we added how many carbons? 3 more carbons, and we only know how many ways do we know to form carbon-carbon bonds? Just the one way. Good. We've added hydrogens. We've added a bromine and an oxygen, an OH, right? So we know different ways to add those as well. So we have a choice here, what we want to add first. What would our star material look like? If we're going backwards here, what would the star material have to be? It has to be an alkene, and we're saying even more specifically, a transalkene. Now it's a transalkene because if you look up here, you see this H is coming out at us, and this H is going away from us. So we know that they're in a trans relationship to each other. So somehow in this step we need to add Br and OH, but we'll worry about that later. Right. So what ways do you guys know how to make transalkene? What's the star material for a transalkene? That's the reagents. What's the star material? An alkyne. Has to be an alkyne, right? All right, an alkyne. Good. Now we're back to the alkyne, all the way back to the alkyne. So we say, right, when we make your carbon-carbon bonds, what's the star material for the carbon? What's the star material when we make carbon-carbon bonds? It's an alkyne. What type of alkyne? Has to be a terminal alkyne, right? So it doesn't matter which one we do first. So we replace that methyl here with a hydrogen. And then if we go back one more step, we can go back to our actual starting material. Okay, so now let's look at the forward synthesis. So now we're going this direction. So what's our first set of reagents we're going to need to form this carbon-carbon bond? Na, NH2, right? One equivalent, right? Because we only want to add carbons on one side. And what should our electrophile be? How many carbons are we adding in this first step? 2. Good. So that gets us to, we've added these 2 carbons here. Right? They were right here. So we number them. So if this was 1 and 2, and this is 3 and 4, there is 3 and 4. All right. Okay. So now we need to add another carbon piece. So what's our first set of reagents we use? Step Na, NH2. It's the only way we know how to make carbon bonds. Step 2 would be what? How many carbons are we adding? 1. So it's CH3 Br, and that gets us to this. Remember our carbons, 4, 3, 1, 2. This would have been carbon 5, and now carbon 5 is there. Okay? So far, so good? Now we want to take an alkyne and make it a transalkene. What kind of reagents do we use for that? Na, metal, NH3. All right, that's at minus 78 degrees Celsius. All right? That gets us a transalkene.
Could you also use Lindlar's? Or
No.
there's cis. That's right.
Lindlar's add cis, right? So we couldn't use Lindlar's because that would add cis. Good.
Sometimes if I mess that up. Okay, I got this.
You have to write an equivalent for that, or
No,
no?
it'll stop at the alkene. Yep. So now we need to add a Br and an OH. So what reagents do you use for that? HBr and water would not give us that. HBr and water would give us a
BR2 in water?
HBr and water would give us an H here and an OH here. But Br2 in water, right? Remember Br2 always gives us what kind of product? A trans. And notice, are these two things trans? HBr goes through what kind of intermediate? HBr goes through what kind of intermediate? No, that's Br2. HBr goes through a carbocation, and carbocations are what hybridization state? sp2, so they're flat, so there's no stereoselectivity. With Br2, we always get trans products. So the bromine, and in this case, the OH would always be opposite sides trans to each other. So it had to be Br2 in water for that one.
So then does the water replace one of the...
BRs,
Okay.
yep, that's right. So water replaced one of the BRs instead, because water is the solvent, so there's a lot more of it around. That's that chapter 6 stuff. So let's take a look at a resonance structure. So first things first, let's talk about this molecule. Is this molecule, and is there anything special about this molecule? What are the hybridization states of all the elements in the ring? What are they? sp2, so they're what geometry? Planar. Okay, so it's an uninterrupted pi system. How many pairs of lone pairs are there in there? 3, so this molecule is aromatic, right? As it is right now, it's aromatic. Good. So let's see if we can draw some resonance structures. So the first thing I would do is I would take these 2 pi electrons and give them to the oxygen. Right? So where's there going to be a plus charge now? If I say 1, 2, 3, 4, 5, 6, where should there be a plus charge? What carbon? Carbon 6 should have a plus charge, right? Good. If I want to stabilize that, which pi bond could I move? Between what 2 elements? 4 and 5. So move those electrons there. One, 2, 3, 4, 5, 6. Where should the plus charge be at now? Carbon 4. So now what could stabilize that plus charge in carbon 4?
2 and 3,
The pi bond between 2 and 3. Anything else?
5 and 6.
I could go back to 5 and 6. Yep, that'd be going back towards this. If the pi bond here moved, it'd be going back this way. What else? The what? The what from the oxygen? The lone pairs from the oxygen also could stabilize it. So let's draw that one first. All right. And then again, if we wanted to move, he said the pi bond between 2 and 3, if that moved here, they could allow these electrons to go back to the oxygen. And now where would the plus charge be? On carbon 2. Is there one last resonance structure to draw? The lone pairs from this oxygen can come here. So how many total structures do we end up with? A lot. 6 total. All right. So is this a very stable molecule? Yeah, a lot of resonance structures. It's aromatic. Very stable. Which 2 structures are the best structures? Which 3? There's 3 structures that should catch your eye as being good, and then 2 of those should be the best. So if I label these A, B, C, D, E, and F. Give me the 3 best ones. What are they? What would we be looking for 3 good resonance structures? What's our first rule of the dot structures? Full octets. So which ones have full octets?
Yeah.
A has a full octet. D has a full octet. And F. A, D, and F all have full octets. Now between A, D, and F, which of those are the best?
A and F.
A and F, why? That's right. Why are A and F better than D? What do A and F have going for them that D doesn't? Was the first question I asked you.
If it's aromatic.
Are A and F aromatic?
Yeah.
Yeah. Right. That obviously makes you more stable too.
How don't the other ones have octets?
Because the other ones all have carbocations. If you have a carbocation, right, carbocations don't have full octets. So necessarily less stable. So even though the oxygen has a plus charge, right? First rule of the stock structures is full octets. The second rule, of course, is that they lie. So just because an oxygen has a plus charge doesn't mean it's bad. Full octets is more important. All right, so let's look at if we have a symmetrical internal alkyne and we react it with BH3 and then OH minus. So the first step, we go draw BH3 out. Classic question, what's my nucleophile? What's my electrophile? What's my nucleophile? Pi bond's a nucleophile. So it attacks the empty p orbital for BH3. At the same time, this hydrogen attacks the other carbon of the alkyne. So let's number the alkyne carbons. 2, 3, 4, 5, 6. And remember, carbon 3 and 4 are exactly the same, right? Symmetrical alkynes are exactly the same. So we end up with what kind of addition do we have here? It's always going to be cis addition. So the hydrogen and the BH2 will always be on the same side. Step 2, we have the OH minus, and all that does is replace the BH2, keeping it the cis addition intact. Eesh. All right, and now we're at this point. What does this look like to you guys? Well, what is a functional group? It's an enol, and enols we all know tautomerize into ketones. Let's make sure we number our carbons again, though, so we don't lose track. 4, 5, 6. So it should be a ketone on what carbon? 4. Mm, 2, 3, 4, 5, 6. Good. Okay. An alkyne with Lindlar's catalyst, and the same alkyne with Na, NH3, and again the same alkyne with H2 palladium on carbon. We get 3 different products here. All right, Lindlar's catalyst, take alkynes, first number of carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Lindlar's catalyst can take an alkyne and reduce it to an alkene and stop it there. But it's always going to be a what kind of addition?
Cis.
A cis addition. Good. Number our carbons. 1, 2, 3, 4, 5. All right, so it's a cis addition. Cis. Sodium metal and NH3 liquid ammonia will give us what kind of alkene? A transalkene. Number our carbons again. 1, 2, 3, 4, 5. So we get a trans addition. H's are trans to each other. Now if we have H2 palladium carbon with an alkyne, what do we end up with? An alkane, right? So all we do here,
Does that have any kind of like cis or trans, or is it just?
it adds
doesn't
it adds cis, but at the end of the day, it's not going to matter because, right? Everything went to an alkane, right? So it can't stop reducing.
Is there another reaction where you just have H2? No palladium? Carbon?
Nope.
Oh, okay.
Nope. Won't work with just H2. Need the palladium on carbon, or something to catalyze it. So let's look at if we have a terminal alkyne, and we're going to have it react with Hg2 plus and H plus in water. First step, what's my nucleophile, what's my electrophile? Pi bond's the electrophile, what's my pi bond's the electrophile?
Oh, nucleophile, sorry.
Pi bond's the nucleophile,
And,
Hg is my best electrophile.
yeah.
But like just like a bromonium ion, the Hg comes back and attacks the pi bond, or the alkyne, I guess. We number our carbons, 1, 2, 3. So we form a mercurium ion. And we have water still floating around. And if we number our carbons, 1, 2, 3. So now our water has a choice. Water would be the nucleophile here. The carbon compound with the mercury would be the electrophile. We've decided which carbons we should attack, 2 or 3. Which one are we going to attack? 2. Why?
It's more substitute.
2 is more substitute, so it's more able to stabilize a positive charge. We attack that one. Actually,
Does Hg have a positive charge when it's got 2 bonds?
It
Or
doesn't.
Partial bonds?
it doesn't now. There it did, because remember, it's also donating a lone pair back here as well in that first step.
Oh.
Alright, so we form this enol type thing, where the water, the H will give away, yep, it's trans to each other. That's important. Remember, see, the mercury and the OH are trans to each other. Alright. So now we have an enol, or a mercury enol. So we can tautomerize this. Alright, we can do a tautomerization. And if we remember our numbers, 1, 2, 3. So now we'd have a ketone on what carbon? Carbon 2. Our mercury still on there though, and we want to get rid of that. All right. Mercury's bad news. Bad news bears. So that's when the H plus comes into play. Our mercury can leave. These electrons will go here. This pi bond will go get the H plus. So now we have mercury, H2 plus again. And now we just have a regular old, right, this looks like to what to you guys? What functional group is this? It's an enol. Right, and enols we know we can tautomerize back into ketones. 1, 2, 3. 1, 2, 3. This is also a tautomerization.